Let's talk about vodcast 5.6. We're going to talk about how ions are formed, and to do that we need to talk about something called valence. And you've probably heard this term before. It's one of the things that sort of pops up a lot in vocab when you're doing elementary stuff, or middle school stuff rather. And simply put, valence electrons are the electrons in the highest occupied energy level. Okay, so what does that mean? So let's go back to our example from the last time of oxygen. Okay, oxygen has 8 electrons. Okay, we talked about that. Whoops, that's a negative. Okay, and so we're going to put our 8 electrons in here as we've been doing with our electron configuration. So 1, 2, 3, 4, 5, 6, 7, and then 8. Okay. So if valence electrons are the electrons in the highest occupied energy level, the first thought that someone would have is, you look at this and say, okay, well, isn't this the highest occupied energy level? So wouldn't that make it 4 valence electrons? But what's important is that energy level is not the orbital, okay, which is P, okay, it's the P sublevel with 3 orbitals in it. Energy level is not that. Energy level is the number in front of it, which is the coefficient. And so it's basically everything in the highest occupied energy level. And what does occupied mean? Occupied means it has electrons in it. Like obviously there are a lot of higher energy levels, but they don't have any electrons. So the occupied ones here are just the 2s. And so we're going to add the 2 here to the 4 here, and we're going to get 6 valence electrons. Okay? The way this is typically going to work for us is in almost every case, it's just the s and the p orbitals that are going to matter. And the reason for that is that when we work these things out, remember that like even here when we get up to the d, that this d level is actually in between the 4s and the 4p, but that would mean that d is higher up than 4s, but the highest occupied energy level is then energy level number 4 in that case. Okay, so it would be whatever is in the S and not the D. So it's pretty much always the S and P's, and we'll see that here in a second. Now, the way that we find this typically, rather than just doing a straight-up electron configuration, is this. For non-transition elements, in other words, for things that are not in the D block or even down here in the F block, we're just going to count across the periodic table, and we're going to skip the F block. So what that means for us is that if we just sort of number off the columns, 1, 2, 3, 4, 5, 6, 7, 8, that tells us how many valence electrons there are. Okay, so if we wanted to look at, say, boron, okay, we find it and we would just count across. Like, I mean, obviously I have my numbers here, so we know it's going to be 3. But I would just start at the end of the S block here and count and say, okay, so I've got 1, 2, 3, and so boron has 3 valence electrons. Okay, let me label that just so that we know that that's only valence. Okay, so relatively simple as far as like if you just are looking for things in the S and the P. And to be honest, that's pretty much what we're going to do most of the time. The transition stuff and the F block stuff gets a little bit more complicated. So we're kind of usually going to stick to valence electrons. We're going to use those a lot in the next section when we talk about bonding here in just a minute. But let's just do a couple of others real quick. So magnesium. Let's see, let's do chlorine, let's do fluorine too, and we'll do argon. Okay, so let's just look at these real quick. So we just want to sort of count across until we get to each of them. So magnesium is right here, so 1, 2, so magnesium has 2 valence electrons. Okay, chlorine is over here, so we 1, 2, 3, 4, 5, 6, 7. And when you're dealing with stuff that's on the extreme left-hand side of the table, what often is easier is if you start here at the last block where the noble gases are and count backwards from 8. Okay, so we're going to do that for our next one. So like fluorine is what we want to do next. And so I'm going to count 8, 7. And so that gives me 7. You'll notice that chlorine and fluorine both have 7 valence electrons. That's why they react the same. Is that ending electron configuration is the same. The 7 valence electrons is the same. And then if we want to do argon, it's at 8, so I don't really have to count backwards. But just to be sure, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8 valence electrons. We'll also see here in a minute that that's kind of the magic number for valence electrons. That's what everyone wants to have. Okay, so valence electrons, why is this so important? Because in the outer shell, every atom wants to get to 8 outer shell electrons. It wants 8 valence electrons. And that rule has a special name. We call that the octet rule. Okay? So it's pretty important. I like how I highlighted that and then it turned it a color opposite of the color. So that's pretty cool. So the octet rule basically just says that they all want to have 8 valence electrons. So if they don't have 8 valence electrons, they try to find some way to get there. So like if you look at this, so boron has 3 and magnesium has 2, chlorine and fluorine have 7, argon has 8. It's happy according to the octet rule. Fluorine wants 1 more, chlorine wants 1 more. Magnesium either needs 6 more or can lose 2 and drop down and have 8. Same thing for boron. It needs to get 5 to get to 8, or if you lose the 3, then you get to 8. And the way that typically works is that things that have 4 or less are going to lose, and things that have more than 4 are going to gain so that they can get to 8. Okay, so let's real briefly talk about sort of how that works and just to see how that's going to come out. We'll jump back to that slide here in just a second. So we've got 2 elements here, sodium and fluorine. Okay, and so if we real quick just determine their valence electrons, we can determine it in 2 different ways. So first off, the highest energy level for sodium is 3, and so it has 1 valence electron. Okay, and fluorine over here, the highest energy level is 2, and it's got 2 in the 2s and 5 in the 2p, so that means it has 7 valence electrons. Okay, now some of you may be already able to see where this is going. Fluorine needs 1. Sodium, if it gets rid of 1, is probably going to have the right valence, and we'll talk about that in a second. Oh, hold on, there's a giant typo in this slide. That is terrible. Hold on, let's fix that real quick. Oh my goodness. Can't have that. Okay, now we're okay. So if you look at the drawings, you can sort of tell the same thing. How many electrons are in their outermost shell? Well, sodium has 1. Okay. Fluorine has 1, 2, 3, 4, 5, 6, 7. And so what happens very often in compounds, and this is an example of what we call an ionic bond, we'll talk about those in the next unit, is that sodium is going to give up its electron. Okay? And now what happens is that instead of having just 7 valence electrons, that fluorine now has 8 in its outer shell. Okay, count around again the outer shell. So 1, 2, 3, 4, 5, 6, 7, 8. And what this means is that this is where fluorine was. Fluorine had 9 protons and 9 electrons, but now it doesn't have 9 electrons anymore. Now it has 10 electrons. Okay, which means that its charge is no longer balanced. I have 1 more negative than I have a positive, and so what that means is the fluorine is going to have a 1 negative charge, or a -1 charge. Okay, now, so fluorine's all fat and happy now. It's got its 8 to satisfy the octet rule. So you go back over here to sodium, you're like, the sodium doesn't have anything now. It's not very happy. Remember that valence applies to the highest occupied level. Okay, so what that means is that if I get rid of the electron in the 3, okay, then that 3 isn't there anymore, so that's not the highest occupied level. Now the highest occupied level is the 2s. And how many does it have in the 2 level? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what happens to the charge on sodium then? Well, sodium had 11 protons and 11 electrons. Now though, okay, it doesn't have 11 electrons. Remember, it gave 1 away. It has 10 electrons. Okay, so now what happens to its charge? Well, now it has a +1 charge because it's got 1 more proton than it has electrons. Okay, so real quick, let's talk about the names for those things. So ions are atoms that have positive or negative charges. Okay, cations have a positive charge. All right, they're going to lose electrons, which gives them a positive charge. You tend to think that if you lose something, you should have a negative charge, but remember, electrons have a negative charge, and so if you lose them, then you have more positives than minuses, just like in your sodium. And you might want to rewind back just to look at that. Anions have a negative charge because they gain electrons. So fluorine is what we call an anion because it has gained an electron. Now it has a -1 charge. Okay, and real briefly, and we'll get to this a lot in the next chapter, but real briefly, metals tend to form cations, okay, and nonmetals tend to form anions. Now, this is not absolutely always strictly the case, but that is generally the rule. And the reason for that, if we jump over and look at our periodic table real quick, is that, remember, here's the staircase. Okay, so let me draw that in real quick just to make sure that everybody knows where the difference is. Okay, so staircase. Everything to the right of this is nonmetals. Everything to the left are metals. And the way it works is that if you remember our labeling of valence, so 1, 2, 3, 4, 5, 6, 7, 8. The way it works is that metals tend to have less than 4 electrons. And if they have less than 4, remember, we said that they give them up. And if you lose electrons, you become a cation. Nonmetals have more than 4, and that means that they're going to want to gain electrons. If you gain electrons, you get a negative charge, and you therefore become an anion. Okay, we're going to talk a lot more about ions when we do bonding in the next unit, especially obviously ionic bonding. But I thought it was important for you right now when we're doing electron configurations to realize what happens to form these things. And so real briefly, let me just sort of show you what this does to the electron configurations now, because I sort of crossed that out. But what this means is that a sodium with a positive charge now doesn't have 11 electrons, it only has 10. And so that changes its electron configuration to become this. And likewise, now that fluorine has 10 electrons, it changes its electron configuration to become this. So we gained an electron here, we lost an electron here, changes their electron configuration. Now you're looking at these going, oh my gosh, they're both the same. They are both the same. That's just sort of a coincidence from the two things I picked. They don't have to be. But what does have to be the same is that their outer shells should then have 8 each, which they do. All right, guys, thanks a lot. If this was a little confusing, just make sure you go back and review it, and I think it should all become clear.